In our previous activities with polynomials, I've either given you a graph with very clear zeros that you could turn into factors, or I've given you a polynomial in factored form from which you could find the zeros. But what if you're given a polynomial in standard form, not factored, and there aren't enough zeros on the graph to determine all of the factors? Well, we are going to look at how to find all the zeros of as many polynomials as possible. There are polynomials for which we cannot find all of the zeros, and that's what it says under method 3 on the first page of the notes. But for ones that we can find all of the zeros, we're going to learn some techniques. So first of all, we have a cubic here, x cubed minus x minus 6. If you look at the graph, which I have shown, you'll notice the characteristic shape of a cubic. You'll also notice that it only crosses the x-axis once, and that point is identified as the point 2, 0. So we know that one of the zeros is 2. However, the other two zeros have to be imaginary because the graph does not curve as it crosses through the x-axis. Therefore, that's not a repeated zero. And as a matter of fact, the curve occurs down here, which is another indication that there has to be some imaginary zeros. So how do we find those imaginary zeros? We start by using the zero that we know and doing synthetic division. So we're going to put 2 in here and list the numbers 1, and as we have 1x cubed, 0x squared, negative 1x, and negative 6. It's very important to remember that 0 placeholder for the x squared term that's missing. Bring down the 1, multiply by 2, and add, multiply by 2, and add, multiply by 2, and add. Now, if 2 is really a 0 of the function, then I have to get a remainder of 0. If this had not ended up equaling 0, then I did something wrong, because I already know that I should get 0 for y when x is 2. Now, what does this leave me down here? Since I started out with a cubic, this is a quadratic, x squared plus 2x plus 3, which means this whole polynomial factors to p of x is equal to x minus 2, that's because we know that 2 is a 0, times x squared plus 2x plus 3. So to find the other two zeros, I just need to find the two values of x for which this quadratic factor is equal to 0. X squared plus 2x plus 3 equals 0. If it factored, I would have already been able to find those zeros probably a little more easily. So we're going to assume, no, this doesn't factor, so I'm going to have to use the quadratic formula. So x equals, here a is 1, b is 2, c is 3. So x equals negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 3 all over 2a. Remember our little song. It's good to remember that. So this is negative 2 plus or minus the square root of 4 minus 12. So this is negative 8. Oops, I wrote 2a, which is just 2 because it's 2 times 1, all over 2. Or negative 2 plus or minus. Now I could simplify this to the square root of 2 times the square root of 4 times the square root of negative 1. Well, the square root of negative 1 is I. The square root of 4 is 2. So this is going to be 2I, the square root of 2, all over 2. And then if I divide both terms, let me split this up. So that's negative 2 over 2 plus or minus 2I, the square root of 2 over 2, which would reduce to negative 1 plus or minus I, the square root of 2. So those are my other two zeros. So I have my three zeros are 2, negative 1 plus I, the square root of 2, negative 1 minus I, the square root of 2. Now I can double check to see if that number is a 0 by plugging it into the original function. So if I do f of negative 1 plus I, the square root of 2, that means I would be plugging that in for x in the original function. And I guess it should say p of, because my original function was a p of x. So p of negative 1 plus I, the square root of 2 squared, or cubed, sorry, not squared, cubed, half point for me, minus negative 1 plus I, the square root of 2, minus 6. Now how would I want to do this on the calculator? I would probably type in negative 1 plus I, the square root of 2, and store that first. So let me open a calculator page. So negative 1 plus the square root of 2 times I. Remember, you have to use the little button that has the pi on it and use the I from in there to get the imaginary unit. Then I'm going to store that. We'll store that to x. Where's my x? There we go. And then I'm just going to type in x cubed minus x cubed minus x. I always tend to do that. X cubed, I got to arrow over, minus x minus 6, or was it plus 6? I don't remember my original problem. I better look at it. Minus 6. Okay. And push enter, and notice I get 0. So I've verified that that is indeed a 0. I'm not going to go through that verification process every time with you, but that's how you would double check. And that equals 0. So check. So these are my zeros. I successfully found all 3 zeros. Notice that the imaginary roots occur in conjugate pairs. Okay, on to example 2. Example 2 is a 4th degree polynomial. Notice that we see some roots here. We see 1 here, we see 1 here, and we see 2 here. Now, it's kind of hard to tell from the graph. Is this a double? If this is a double 0, or if it's 2 individual zeros that are really close together. This is one where we might be able to find one of the roots just by looking at it, but we're going to have trouble finding all of the roots. This one appears to be the first one to the left here appears to be in between. Let me get my little cursor going. In between 2 whole numbers. This one appears to be at -2, and this was in between 0 and 1. So there's a couple ways I can find that 0, but I want to talk a little bit about the rational root theorem before I go on. The rational root theorem says that I can look at the coefficient of the leading term and the constant, and I can figure out all of the possible rational numbers that could be roots. Remember, we can have real numbers that are roots. They could be either irrational or rational. The irrational ones generally that we're going to be looking at involve the square root. But I'm assured that no other numbers besides these numbers can be rational roots. So let's think about why that is. If I were to factor this polynomial into linear factors, we would have a 2 out front because my leading coefficient is 2, so I could basically factor that 2 out of one of the factors. And I'd have x plus a, x plus, well, let me just write a blank, x plus blank, x plus blank, x plus blank, x plus blank. Now you realize that blank could be either a positive or a negative number. Now, these numbers all have to multiply together to give me 2, because 2 times all of that number then would be 4. So basically all of these numbers have to be factors that when multiplied together add up to, or multiplied together, I get a sum of 4. Because I'm multiplying by 2, some of these numbers could be fractions with 2 in the denominator, because if I multiplied 2 times 1/2, for example, I would get 1, which is a factor of 4. So that is the reason for the way the rational root theorem is. The rational root theorem, or the rational zero theorem, says that all possible rational numbers are factors of the leading coefficient divided by factors of the constant. And so factors of the leading coefficient are plus or minus 1. I'm sorry, other way around. Factors of the constant divided by factors of the leading coefficient. I'll just put LC. So that's going to be plus or minus 1, plus or minus 2, and plus or minus 4. All of those numbers divide evenly into 4. And then I have plus or minus 1 and plus or minus 2 as factors of 2, which is the leading coefficient. If I look at all of the possible combinations, all of those numbers in the numerator divided by 1, all of those numbers in the numerator divided by 2, I end up with these 3 numbers, or these 4 numbers. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 1/2. So that gives us a little bit of a clue. Notice that this number is -2 here, or appears to be -2, and it looks like this could be -1/2. So those are possible rational roots. If we can find those two of those numbers exactly, we'll be able to divide down our polynomial into a quadratic and then easily find the other two with the quadratic formula. So I'm going to go to the calculator and take a look at this graph, because we can trace the graph to find some of these values. So here's the graph that I have here. If I go to menu, trace, graph trace, oh my word, my Windows things went haywire on me. Let me just use my arrow keys. If I do some arrow keys, okay, notice there's a 0. And let me move this out of the way. We have a 0 at -0.438. Well, that's not one of the rational numbers that I found. If I keep going, there's another 0. So we have a 0 at -0.5. Also, that answers the question, is that a double 0? No, it's just two zeros that are really close together. One, there's our y-intercept. This is nice about the Inspire, is that it actually finds some nice numbers for you. Now it's not finding them for some reason. It's finding a minimum. There's a 0 minimum. Okay, there's the 0. So -1/2 is a 0, and -2 is a 0. And then if I go on and look at this other 0, notice that is also not a nice number, -4.56. Notice that this number doesn't show exactly 0. This is what I was talking about on the first page. Sometimes your calculator, especially when dealing with irrational zeros, can't quite get this to be 0, but -9 times 10 to the -11th is a very, very small number, very close to 0. So let's go ahead now and go back to our problem. And we found two of the zeros. So by tracing, we found that -2 and -1/2 are zeros. So what we're going to do is divide the polynomial by each of those numbers. So we're going to start by putting -2 in here, and we have 2, 15, 31, 20, and 4. Bring down the 2, multiply by -2 is -4. Then we have, oops, I wrote -2. -4, and then this would be 11. -2 times 11 is -22. Add, this would give me 9. This would give me -18, which gives me 2. -2 times -2 is -4, which gives me 0. And remember, I have to end up with 0. Now, what I've divided down to now is from a quadratic, a 4th degree, I've divided to a 3rd degree, which is 2x cubed plus 11x squared plus 9x plus 2. Remainder 0. So when I divide by the next 0, I'm not going to go back and divide the original polynomial. I'm going to divide the next step down. I'm going to divide the cubic now to get it down to a quadratic. So I'm going to put -1/2. And yes, you can do fractions in here, and they're not bad at all. This is 2. -1/2 times 2 is -1. Then I get 10. -1/2 times 10 is -5. When I add, I get 4. -1/2 times 4, -2. I get 0. So I have successfully divided this down to 2x squared plus 10x plus 4 equals 0. So my polynomial, and did I call this one p of x? This is f of x. F of x can be divided into x plus 2, x plus 1/2, those are my first two zeros, and 2x squared plus 10x plus 4. Now notice I can factor a 2 out of that last factor. So I could actually write this as 2 times x plus 2 times x plus 1/2 times the quantity x squared plus 5x plus 4. Now does that factor again? It looks like it does, but I don't think it's supposed to. Did I do something wrong? X squared divided by 2. I'm going to have to pause a moment and double check this. You all are probably screaming, half point, half point, half point by now because you figured out what I did wrong. I just now figured out what I did wrong. This should be a 2 here because I knew that the answers weren't coming out the way they were supposed to. Now, x squared plus 5x plus 2 is not factorable. If it was factorable, I would have found 2 more rational zeros, but I didn't. I only found those 2. So these have to be irrational or imaginary zeros. Now we can tell which ones they are. They're not imaginary because the graph actually crosses the x-axis two more places. We found them when we were tracing. So they have to be irrational numbers, real numbers but irrational. So let's find what these two are. Using the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Don't you love to hear me sing? It probably makes your day, doesn't it? Negative 5 plus or minus the square root of 25 minus 8. 25 minus 8 is 17 all over 2. Not a nice number, but not an imaginary number. So our other two roots are negative 5 halves plus the square root of 17 over 2 and negative 5 halves minus the square root of 17 over 2. So let's just check one of those numbers. If we go back to our calculator, well, when we traced this, we found out that this number was, the 0 here was negative 0.438. That was one of the ones. That would be the smaller of the two negative numbers, so that would be this one right here. So I'm going to just do a quick calculation. Negative 5 halves plus the square root of 17 over 2. Actually, now that I'm in the trace mode, I could just type that in while I'm tracing. So negative 5 divided by 2 plus the square root of 17, arrow over, divided by 2, and push enter. And look at that, that gives us one of our zeros. There's the negative 0.438. So we've double checked that that is indeed a zero of the function. So there is the irreducible factorization, and this is when we cannot reduce it. And if we were to write this as linear factors, we would write it like this. F of x is equal to 2 times x plus 2 times x plus 1/2 times x minus the quantity negative 5 halves plus the square root of 17 over 2 times x minus the quantity negative 5 halves minus the square root of 17 over 2. This would be written as linear factors. The line above, this is linear and irreducible quadratics. Oops, I can't spell this. Irreducible quadratic. Okay, so that's, both of those would be nice. This is usually the irreducible quadratic is the nicer way to write the factorization, but this shows that it can be written indeed as 4 linear factors multiplied together. All right, on to the next one. Here we have, when you first graph this, if you do this on your calculator, you would get a window that looks blank, and hopefully you would be smart enough to realize that you just need to change the window settings. As a matter of fact, I should talk about that. Every one of these graphs that I've displayed, when you first type them in, you're not going to see all of the curves on the graph. For example, here, notice that I had to change y minimum to negative 35 and y max to 20 to see all of the curves on the graph well. On the first graph, I had to change, I had to actually zoomed in a little bit, I made my y min a little bit lower, made my y max a little bit lower, zoomed in a little bit on my x's. You'll have to do some changing. Plus I went in and I changed the window settings so my tick marks on the x-axis would equal 1 so you could see where they crossed better. So I did a lot of adjusting on window settings when I made these graphs. So here I just wanted to point out that you wouldn't see anything because notice x to the 4th and x squared will always give me positive numbers. So if x is 0, y would be 9. That would be my y-intercept. Any other y values are going to be bigger than 9. So when I look at 6.67 here at the top, it's not even showing me the lowest value of the graph. So I had to move my y max up and make it bigger to see the graph. It looks very much like a parabola, and x to the 4th graphs can look like parabolas, but we know that it's supposed to have 4 zeros. Yet it doesn't cross the x-axis at all. What does that tell us? Yes, you guessed it, they're all imaginary. Now, if I don't have any zeros to go by at all, how can I divide this down into using a quadratic using zeros to find what all the zeros are? Well, most of the time, if it's an x to the 4th and they're all imaginary, I can't do anything. I can't find them at all. However, there are some quadratics, some fourth degree functions that are in quadratic form. Notice we have an x to the fourth, an x squared, and a 9. We don't have an x to the third or an x term. If we don't have those terms, then we have what's called a fourth degree that's in quadratic form, and so we can factor it as if it were quadratic. So this involves just straight factoring skills. What I have to do is make two parentheses. This would be an x squared, and this would be an x squared, and the last two, these new numbers have to multiply to give me 9 and add to give me 6. So this would be plus 3, plus 3. So notice that I have some identical things here. Now how do I find the zeros? I set each of my factors equal to 0. X plus 2 squared equals 0. I'm sorry, x squared plus 3 equals 0, or x squared plus 3 equals 0. Obviously I'm going to get the same answers for both of those. So x squared equals negative 3, x equals plus or minus the square root of negative 3, or plus or minus the square root of 3i. So what are my zeros? My zeros are negative square root of 3i, positive square root of 3i, negative square root of 3i, positive square root of 3i. So I have some repeated imaginary zeros. So obviously it can be written in factored form like this, which I already did, or I could also write it out as a bunch of individual factors. F of x, oh, I just turned to red, is equal to x plus the square root of 3i, x minus the square root of 3i. Notice we have a difference of two squares, but when we have a difference of two squares and they're imaginary, it turns out looking like the sum. So we have x plus the square root of 3i and x minus the square root of 3i. So that would be the linear factorization of this polynomial. One more example. This is one that has a double 0. And I'm just going to tell you that for sake of time, that if we do the rational root theorem, we find out that we have possible rational roots of plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, which are all factors of negative 8 divided by factors of negative 1. You can see that plus or minus 8 aren't possible factors, and and these are all whole numbers, so the only possible rational 0 can be here, and it happens to be negative 2, and there's two of them. We have a double 0 at negative 2. So how do we handle a double 0? The same way we'd handle two individual rational zeros. We do synthetic division twice, but with the same number. So this is negative 1. We have a 0 for our x cubed term, 10, 8, negative 8. Drop the negative 1 times negative 2. This is 2. Add. Negative 2 times 2 is negative 4. Add. This would be negative 12. Add. Positive 8. We get 0. Then we do negative 2 again. And bring down our negative 1. We get 2. This becomes 4. Negative 8. Negative 2. Positive 4. 0. So we end up with negative x squared plus 4x minus 2. And to find the other two zeros, which happen to be irrational numbers, not imaginary, because we do see two other places where the graph crosses the x-axis, both positive places, we can find the other zeros from here. So using using quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac. And remember, that's a negative 1 and a negative 2 here, all over 2a times negative 1. So we have negative 4 plus or minus the square root of negative 4 times negative 1 times negative 2 is negative 8. So we have 16 minus 8, which is 8. And this is over negative 2. So we have negative 4 plus or minus, well, this is 4 times 2, square root of 4 times square root of 2, so this is 2 the square root of 2 all over negative 2. And if we separate this, this is negative 4 over negative 2 plus or minus 2 the square root of 2 over negative 2. So we end up with 2 plus or minus the square root of 2. So those are my other two roots. So my zeros are negative 2, negative 2, 2 plus the square root of 2, 2 minus the square root of 2. So 2 plus the square root of 2 would give me this one right here. This would be 2 plus the square root of 2. And you can type that in to double check it. And this would give me the 2 minus the square root of 2. Would give me that 0 right there. So there's 4 examples. I didn't give you an example of not being able to find the zeros at all, because that would just be a matter of using your calculator and finding zeros, which I think you are able to do. I did want to demonstrate, I guess, one time showing you how to find a 0 on your calculator. So if I wanted to do this one, find zeros, let me escape out of here. This was, actually we'll go to the last graph since that's the one I just did. If I wanted to find zeros, you go to Menu, Analyze Graph, 0, and you see this dotted line. If I move, I want to move the dotted line over to the left of one of my zeros, so I'll move it right here because I want to find the 0 that's between 0 and 1. I'm going to push Enter on my calculator. Then I'm going to use my arrow keys to move that line to the right. Then you'll see that a 0 shows up, and as soon as a 0 shows up, push Enter, and it gives you the value. So if I do 2 minus the square root of 2, that's the number I would get is 0.586. So there's how to find a 0 on your calculator. If you are having trouble with factoring, remember you can look at the How to Factor Polynomials, or I guess it's called Factoring Review video. So I would highly suggest that you do that because you are going to need to be able to factor to do these problems. Hope you had fun and you're ready to do your homework. If you have any questions on any of these problems, please write them down and I will talk about them in class tomorrow. Thank you.